this systems business, if I were to pick one of the topics, like I told you guys, I don't think you go to school to make it because it's applicable and you're going to use this in the real world type of things. You're learning how to figure stuff out in a lot of different languages and a lot of different contexts. So the more you learn, the better you are to deal with all kinds of world's issues. This one, however, there are these places that people really do solve systems of equations, and they just either use a computer and how they enter it into what's called a matrix, or they use graphing and those, like I showed you before. I mean, very literally. They don't even change it up a little bit. It's like you're going to school and you apply it. So it's a rare case that this is cool. So the first thing is, if you look at this first one, it is one we can do by substitution, and it's my favorite. It's called like the cascade of substitution. Check this out. We could put the z equals 3 in for the z above. So we can plop that in there, and you get what? Y minus 2 times 3, and that's negative 7. All right, great. That, of course, is, that was weird. Put a minus and an equal sign together. Hang on, there we go. But y minus 6, and so you add 6 to both sides, and if you're following along, that means y must be negative 1, right? So we got y equals negative 1, we got z equals 3, and we could drop both of those into the first equation and then go solve for x. So I think of it as like a cascade, as in like water falling down a mountain. It's like, or a snowball effect. One leads to the solution of another, which leads to a solution of another. And let's get that x. X would be what? X equals, or x minus, I keep doing that, 2y. And our y happens to be negative 1, plus z. Z happens to be 3. And then we find out what x is. So that's x plus 2 minus a negative, plus 3, equals c. And these are, what, 5 together. If we subtract 5 from both sides, we get x is 2. Kind of nice. And this is also, can be written as a coordinate point, but this would be a little bit different, the way these are drawn. This is a plane, not like an airplane. Like, it's a plane as in a flat piece of paper if you graph it. So there's an x, y, z. It would be a flat plane. This one is a line. And this one, of course, is a horizontal line, or some type of line, actually up the z-axis. It's also a line of some kind. But what you do is, if these three things intersect with each other, they would intersect at a singular point in the three-dimensional plane, and we write it as an x, y, z point. We do 2 for the x. You always write it in alphabetical order. And then you do the y, which comes next, negative 1, and then z would be 3. So it's still an intersection. It just gets harder and harder to graph. This would be a plane, a line, and another line, and they would meet at a single point. 2, negative 1, 3. It's the x, y, and z that produce what you see here, 7, negative 7, and 3 simultaneously. So it's the solution to the system. It was awesome. It worked well. Substitution's great. We finish every matrix problem with this process. So every time we solve a matrix that's more complicated, we will end with this cascade of substitutions, one into the other to the next. So get ready to do this over and over and over again. Now down below, like purple. Let's go purple. This one here, we're going to use matrices on. I'm going to show you how to make a matrix. So your first go at matrices, and I feel bad, Anna, you're doing awesome. Hold that thought. I don't want to ruin it, but come on over. I don't want you to miss matrices, and then we're going to look at what you did, which is like a miracle. This is fun. Because when we're done, I think that's going to be really awesome. Fun. But I don't want you to quit yet. Check this out. This is called a matrix, where I'm going to take away the coefficients that are on the x, y, and z, and we're basically going to do elimination over and over and over again. And like I said, we'll finish with substitution like we did up here, but we start with elimination on a really high scale. Here's how it is. You line up your x, y, and z, and you notice I don't have a z in this one right here, the top equation. I'm actually going to rewrite that equation as x minus 2y plus 0z, and then I'm okay. And watch what I'll do. I'll line up my x's, my y's, my z's, and then my stuff after the equal sign. We'll go over on this side. The matrix is just a way of organizing the coefficients. So it'd be 1, negative 2, 0, and 0 in the first row, because the coefficient on the x is 1. Then it's negative 2. and then of course the 0 for the z. So here's the coefficients that I'm plugging into the matrix. You only put the coefficients, and everybody just knows, since you're lining up x, y, and z, that anything in the first column is an x, second column is y, third column is z, and then on the end is numbers. This is called an augmented matrix. I'll tell you what's augmented. It's augmented because it's not square, but don't worry about the definition at this point. But sometimes you'll hear, hey, come up with the augmented matrix for the system. It means line up your x, y, z's and whatever variable, and your numbers, and equal signs, they're always equal. Then put all the coefficients, and don't write x, y, z and the equal sign. You just kind of remove the complication. The next row, we'll go right here so you can kind of see the coefficients here are 1, 2, -1, -1, and then the bottom row, let's go orange, and -3, -4, 3, 5. It's organizing the system